Hello guys, I made a little video here so we can have a proper debriefing, I suppose, and also so that I could get a proper chance to actually explain my idea on the two candidate problems that I proposed, which are the lathe machine and also the vice clamp. So let's start. Let's start off first with the option that I think has the majority of votes, which is the lathe machine. So the cool thing about the lathe machine, right, is that when we open the headstock, we can see a bunch of gears that are really similar to the torsion problems that we were able to solve, right? Like just one look at the gearbox here already looks pretty similar to these, right? Where we have like two different shafts, or three in this case, three shafts, but two shafts will have some points of contact in between, with the use of gears, right? And just looking at it, it looks like we're gonna have a pretty easy, smooth time doing it, right? But I think there's actually a little bit of a problem, and it's basically because of the fact that lathe machines are spinning, right? Like they're always moving. But the problems we've been solving in mechanics, like all the torsional problems we've been solving in mechanics, are static. Let me explain. Let's take a look at our typical problem in torsion in mechanics of materials. So as you can see, all of the forces here, or no, all of the torques here, they just end up summing or netting to a net torque of 0, right? 6 plus 14 minus 26 plus 6 is just 0. And that makes sense once again because the entire system is static. The problem is, however, lathe machines aren't really static, they're moving all the time. So this all boils down to a problem of how are we gonna make a mechanics problem out of a scenario where shit isn't static. So I'm gonna explain a little bit more about this dilemma or problem, and it'll eventually lead to another solution I have in mind. However, if you aren't really interested in me yapping about it, and you kind of just want to get to the point, just skip ahead to the next section of the video. Okay, still here? Cool. So, let me ask you a question. Have you ever felt that the problems they ask us to solve for the torsional systems are kind of weird? I don't know about you, but me personally, I've always found them to be a little weird. And every time I'd look at the example problems and the drawings of the gear systems, I'd always just end up asking myself like what the fuck is this system, bro? Like who would design this? And let me explain. In most problems like this, we have such an elaborate system of gears, and we're applying torque, la-di-da, and all of that effort just to end up being sent to a fixed shaft. As you can see here, connected to two solid steel shafts, A, B, and C, D. Isn't that a little strange? Normally you'd think that people would make torsional systems to make stuff move, right? I mean, think about it. We want to make the wheels of a car spin. We want to transmit the power of a turbine in our Rankine cycles to a generator so it generates electricity. Or in the case of our candidate problem, we want to spin the lathe. And so, if the purpose of a torsional system is to get shit spinning, then why the fuck are we solving problems where shit isn't moving, right? Oh wait, also, I apologize for my language, but I feel the need to exaggerate the points that I'm making. Anyway, as it turns out though, these problems aren't actually that far off. These are actually pretty realistic scenarios that engineers have to deal with. These problems actually represent the cases where the machines might encounter failure or resistance. For example, take the wheels of a car that stops spinning because of brakes, or if they end up jamming on something on the road. Normally when the wheels are moving, we're transmitting a lot of power to get it moving, right? However, when it gets stuck, or if you want to apply the brakes, the wheel will jam, and then all of that torque, which came from the engine, and we want to transmit all the way to the wheels, it just ends up getting sent to a fixed shaft because again, the wheel got stuck, or it's on brakes, or it got jammed, right? And the wheel becomes a fixed shaft because the wheel jams, because the wheel stops moving. And so no matter how much torque we supply to the wheels, it all just ends up sort of being like a fixed shaft. And in the case of our lathe, Its corresponding scenario would be if the lathe gets jammed or gets stuck on something. Or specifically, the spindle, which is the part that holds your workpiece, that's the part that's gonna get stuck at something, right? Like for example, what if you drive your tool bit a bit too deep into the workpiece and the lathe machine got stuck so it stops spinning? Or maybe you didn't put your workpiece properly so it got stuck on something outside and it stopped spinning. And so in those cases, even though we transmitted the usual torque or power into the spindle ended up getting stuck. So it's sort of a representative of a fixed shaft. So whether you're here because you skipped through the explanation or not, my proposal for the solution of this torsion problem is that we just make a scenario or hypothetical of our own where the lathe machine's spindle jams. Because that way, just like I explained a while ago, we quite literally have the regular old torsion problem, where we just send torque to a fixed shaft, right? And so let me further explain. We're gonna have the headstock here with all of the gears inside, and we're gonna be transmitting all of this torque into the spindle here at the end. And then, in that moment in time where the spindle jams, we just think of the spindle, like the shaft of the spindle, as a fixed shaft because it's not moving. And then after that, we just get to solving. So if we do decide to use torsion as the assignment, then this is my proposal. However, I think there is still one more concern. And basically, it's a matter of skill issue. I'm kidding, sort of. I'm gonna be honest, I'm not the best with torsion problems, because if I look back to my score on the quiz or the midterm with the torsion problems, like, whew, I don't even want to think about it. But no, I'm kidding. I actually do have a legit concern. And that's because I'm a little intimidated by the gear system in the lathe machine. You see, I'm not an expert on gears, right? Like, obviously. And if someone were to ask me what's really happening here, I don't know. Like, I just would not know shit, right? But if I look at the gears on the bottom two shafts, I can kind of understand what's going on, right? I mean, this looks like the exact same thing as the torsional problems we've been solving all the time in mechanics, right? But what I'm confused about, is the middle part here where we have the belt in the middle. And I think you kind of know, you know what I'm going with this. That means that if we try to analyze with the lathe machine, we're gonna have to apply belt friction because this is a belt, man. And the thing is, the belt, when it comes to the generation of power of the lathe machine, I don't know which shaft starts it. Like, does the power start here or does it start here? If it does start on the top shaft right over here, then I think we're really fucked because the top shaft here has the belt friction. I'm pretty sure that's where it starts. And so again, if we have to deal with the belt friction, we're gonna have to apply some dynamics to it, right? The worst part is it's not even the easy kind of belt friction. It's the kind of belt friction with a groove in it, like the one with the sign of alpha over 2, if you can still remember from your dynamics class. So if we really want to 100% analyze this, we're gonna have to go run through that problem. And I'm just gonna be completely honest with you. I don't really know how to calculate that stuff, right? Because again, I'm not an expert in lathe machines. I don't know what's really going on, and so I think this is gonna be surprisingly complicated. And I think we might not even have what it takes to deal with this right now, considering all the exams and stuff we have to do, right? So if we want to go through with the lathe machine, like 100% analyze it, budget with a belt, we're either gonna have to do a lot more research than we thought, or we're gonna have to grovel and ask for consultation from a teacher who knows about lathe machines. Okay, so on to the next. The next one I have in mind is, as you know, the vice clamp. Now I'll start off first by saying that I'm really biased in favor of the vice clamp because I think it has the best mix for complexity and feasibility, especially within the time frame and the deadlines we have. So the vice clamp can be very easily represented as one of those problems with combined stresses. One of our latest topics, the combined axial and flexural loads, right? So let's take a look at this FBD that I've drawn here along with the image of the vice clamp. So as you can see here, there's basically uh, one fat support here, which is right here on the FPD, and we also have some masses. This mass over here, which causes a force downward, right here on the FPD. This hanging thing over here, which also causes a force downward, and also this mass, which causes a force downward. And so I think you know where I'm going with this. Like, we can just use the given forces to, say, calculate the maximum stress at this section AA over here in the free body diagram. And in that sense, or in that regard, I think it's really feasible or super easy to do. Like, this is very, very doable. It might even be on the border of like being too simple. However, I think the slight bit of complexity it has is the support here. I mentioned that there's a singular support, right? The thing is, when we solve problems like this, we're very used to having point supports at one point. I don't know if you could tell, but this is definitely not a point. That support is like as fat as the moon or whatever. It's really wide, so I don't really know how we're gonna deal with that. But I'm sure we can just ask Sir Luz Aseguro about how we're gonna deal with that in the calculations. And so that's basically it. And all I have to explain for the two candidate problems. However, I do have one final concern, and that is the group itself. And don't worry, I also have a solution for this. The problem is that I think 15 people in one group is just way too much. It just makes the delegation of tasks kind of annoying and hard to deal with, right? Because again, you're gonna get graded depending on how much you contributed to the problem, right? But imagine having 15 people all working on just one problem. I think we're gonna have a hard time trying to deal with that. And if you think about it, like, again, it's just one big problem. And just thinking about delegating the tasks, I mean, off the top of my head, I can probably think of three different kinds of tasks. Like, one group for measuring and gathering the data on the structure, another group for actually solving it, and then another group for tying it all together in one clean document for submission. I hope it's not hard for you guys to see how difficult and redundant it is if we have to give those tasks to 15 people. So once again, I have another solution. So you know how we're going through the motions between these two options? Oh my god, the lathe machine or the vice clamp? Why don't we just split the group further into two? One deals with the lathe machine and one deals with the vice clamp. And I know what you're thinking, no, but Sir said we had to use the entire group. I personally think Sir would understand if we tried to explain to him. Especially if, like, class literally tomorrow, I think we can just explain it to him immediately, and I think he'd understand. And besides, if you look at the groupings of the other structures, like from the other sections, there's really like a max of 8 or 10 people per group or per structure. The other cool thing about splitting the 15 people is that we're gonna have two groups of like 7 or 8 members. That's a really good number to split the task. I mean, just think about it. We really only need a maximum of like 2 or 3 people to measure and gather data on the structure in the machine workshop, and then maybe we could have 4 people or 3 people to do the actual calculations, and then we could have whoever is remaining to just tie everything together for documentation. Doesn't that sound pretty good? Because again, if it was 15 people, I think a lot of us would really struggle having to find like a job or a task to do, right? So yeah, that's that. The other advantage of splitting us into two groups with these two problems or examples is that, I'm not really trying to brag here or whatever, but I think I kind of already did a lot of the groundwork here, right? I mean, I've been explaining a lot of ways that we can approach the problem. So no matter what problem we decide to pick, be it the lathe machine or the vice clamp, or if we split up into two groups, it's not really a problem because at least we already have an idea of how to approach it with all the explanation I've been doing. And also, even if we do split up into two groups, I don't see how it would be a problem if we just continue talking to each other and helping each other out in the GC we made, right? Like, we're just 15 people in the class. I don't think we have to make another GC. And so that ends my videos and all of my concerns. In short, I basically just explained how we could approach the lathe machine and the vice clamp. And I must also remind you guys that I think the lathe machine is going to be surprisingly difficult. And I also explained that I think having 15 people in one group is just too much. So perhaps we could split it into two. So please tell me, what do you guys think about that? What should we do? And we really need to start talking about it because the deadline is in less than 15 days. So that's pretty much it. And also, one last thing. If we do decide to split into two groups, I have to inform you guys that I am 100% gonna be on the Vice Clamp group because I'm not touching that lathe machine, man. That is way too scary. But anyway, bye. Thank you for listening.